And can anybody please confirm whether the screen is visible to you or not, which I have shared just now?
Yeah, visible.
Okay. One minute, please. So welcome everybody to this points of topology part 1 live session. So this will be total 12 weeks course, and 1 minute. So I need to know how to add one. Hi. So mm, so this is the first live session of the points of topology 1 course. So this will be a 12-week course. Okay, so the main target of these live sessions are only for mostly of course mostly for problem solving and clearing doubts. Of course we will clear concepts. You have any issue with the concept itself, and eventually we might revise some difficult concepts also. Okay, but the fundamental target of this session is to clearing doubts and problem solving. Okay. So okay, so as per Sastry sir, going he started from nominal spaces. Then after a few days he will start topological spaces. Then after a few days he will start the sorry sorry he so right now he is doing nominal spaces. After a few days he will do metric spaces, and finally he will go with the topological spaces. Okay, so that will be his sequence. So we will follow that. um, but uh, but today we shall start with the metric space, at least from basics, in order to understand what the advantage of metric space is over the real analysis, so that you can get some kind of flavor in the for the topology itself. Otherwise the topology will be very boring. Okay, so
Excuse me,
yes, tell me.
I have a doubt.
Yes,
There is this when we define the non-linear space, we use the triangle equality as a definition.
correct.
So triangle equality is defined for
uh,
valid for
one minute.
non-Euclidean
Sorry,
geometry also.
sorry for interrupt. So what you have said, that triangular inequality is taken to be definition
Uh,
of
One of the
the
criteria,
of non-linear space or metric space? Which one you are talking?
metric space.
Okay, yeah. Now continue.
So that in Euclidean in non-Euclidean spaces, for example, hyperbolic geometry or spherical geometry, the triangle equality is still valid on these spaces. That is my question.
Apart from hyperbolic geometry, you told Euclidean geometry or something. What you told apart from hyperbolic?
Non-Euclidean geometry.
No, non-Euclidean geometry. This triangle inequality will not come into the picture.
Okay. So we just no, metric space approximate the approximation of the non-Euclidean geometry. Mm, localize local in the local space a particular small neighborhood, and this thing looks like a metric space, and metric will define.
No, not necessarily. the, the nomenclature is non-Euclidean geometry, right? So locally it is not look like any Rn. So in general we cannot say like that, correct?
No, but in the definition of manifold,
Yes.
we use we use that locally it looks like a Euclidean in the
Correct,
all books.
correct. But metric space comes under the Euclidean geometry itself.
There is a Minkowskian space-time. There are also a metric also defined on their
Yes,
space.
yes.
Actually, I am from physics background.
Okay.
Uh, so in Minkowskian space-time, there is a there also a notation of metric.
Yes.
that is the non-Euclidean actually. Minkowskian space is non-Euclidean geometry, and when we go to the Riemannian geometry, then it completely has different picture. There is their curvature actually arises.
Hmm. Yes, correct. But as far
So
as
these definitions, what the set told us, this can be extended over the whole whole generalization of this non-Euclidean generalization. That is my question.
no, no, not necessarily, because since it is already non-Euclidean and if it can be extended in general,
Hmm.
so then there is no point of putting the nomenclature non-Euclidean, right? So there is some properties which cannot be extended from locally to globally. Okay.
But at that space in non-Euclidean geometry, we also define the topology also.
Ha,
So
yes.
so to define the calculus or topologies, we have to extend these ideas actually.
No,
Or
for defining topology, I mean, there are spaces. We will see in the course. There are spaces which are topological spaces, of course,
hmm,
but on the spaces it is not possible to define metric.
okay,
So, the spaces, non-Euclidean spaces that which you are talking about. So those are topological spaces, but there is no guarantee that those topology one can get from some induced metric on it. There is no guarantee like that.
okay.
Okay. And also at the same time, one can define some metric on some given space, but there is no guarantee that metric is coming out of some norm defined on that space. Okay. So yeah, so that is the thing. So for example, 1 minute. No, that example right now we are not in a position to discuss that example. We will see in the course. There are certain spaces on which this type of situation occurs actually. Understand?
Okay.
Yeah. And by the way, the Minkowski space which are talking about, it seems that Minkowski, that thing is entirely different from the Minkowski space which we usually see in the function analysis on metric space. Because in metric function analysis, the Minkowski space has a well-defined metric and which satisfies those properties. Understand?
By those properties you mean the set told us in the lecture.
Yes, yes, correct. Those three properties, right? Yes, those
And
three
those
properties.
these properties.
Yes, yes, those three properties only.
Okay, okay.
Understand?
Thank you.
Yeah. So okay, so okay, so this course will be mostly problem solving, but today is the first day, so today we shall first go with the introduction part. So okay, so before 1 minute. How many of you are from um, other than maths background? How many of you are other than from maths background? You can raise your hand. Okay, one. Okay. So yes, lad, you are from which background? You can type in chat also. Mr. Yash lad, you are from which background? Statistics. Okay, okay. And okay, so I can assume the rest are from maths background. So how many are you from undergrad level? Okay. Others, how many of you are from undergraduation level? Okay. Okay, so I can assume that all of you, except Yash, I can assume that all of you are from post graduation or above. Okay, so okay, so 1 minute. Okay, so today we shall. Um, okay, before starting, 1 minute. Okay. Okay, so today, since sir is had has started with the basically the norm spaces, so today we shall start with the metric space. Okay, I shall first introduce the definition of the metric space, and then we will see some examples, and then if you have any questions from sir's session or your own questions, you can ask, or else we can start with our separate questions. Okay, so wait. Okay, one. So So today we shall start with the metric space first. So before going to the mathematical definition of metric space, first let me tell why we need the metric space. What is the importance of metric space in general? Okay. So okay. So meanwhile, if you have any question or any doubt in previous session or your own question, you can stop and ask me. Okay, because this session was for only for mostly for problem solving. Okay. So look, in real analysis we have basically in real analysis we have only one thing, namely the distance between 2 points, namely the Euclidean distance, and those distances satisfy some properties intrinsically. Okay, and upon this one can define open balls, open sets, closed sets, etc. and and upon this one can then consider the compactness, connectedness, all those topological properties. So so in metric space we have, so basically in real analysis we mostly have one thing, namely the distance between 2 points. Okay, so in metric space basically generalizes that in metric space we have some distance function over some space. That is, if you have 2 points, then there is a well defined notion of distance satisfying certain properties, and with respect to those properties one can define open balls, closed balls, open sets, closed sets, closed sets, and with respect to those one can study compactness, connectedness, all those things. Okay, so that is the thing of metric space in general, and of course with respect to that distance definition one can define the sequence, convergence, series, etc. Okay, and so and in topology one and the main difference of the topology metric is that in metric space we first define the distance function. With respect to distance we can define open ball, closed ball, etc. But in in topological spaces we directly declare given subsets, some subsets of the given set to be open set. We declare some collection of subsets of the given space to be open or closed, whatever is necessary, and then with respect to those things one can discuss about compactness, connectedness, closures, etc. Okay, so there are some examples where we can show that the given space one can define a topology on the given space, but that topology is not coming from some metric space. We will see what does it mean by topology coming from metric space or not. And moreover, there are certain metric space on which the given metric cannot be can one cannot get from a nominal spaces. Okay, so this is the main basic difference of these things. And and yeah. mm, um, okay, so that's for the introduction purpose. And one more thing is that basically, um, in so since this course is a points topology course, so one can directly start with this topology, but that will not give any mm, difference between direct difference between real and instance topology. That's why first we shall go through the metric space, at least basics, and try to solve some basic problems. Then we shall gradually go to topology and these applications. Okay, so first few weeks we shall stick to topology and also the nominal spaces. Then we shall gradually go to topological spaces. So um, okay, so okay, so before starting the definition with the metric space, let me know, do you have any question or any concern regarding this course, or do you have any doubt regarding this course? If you have any doubt, any question, any concern, you can tell me or ask me. And also, since at least two of you are from different background, so if you have any, so whenever if you feel there is something you did not get properly, please stop and ask me, because these sessions are for problem solving and doubt clearing sessions, so don't hesitate to ask. Okay, so before starting, let me know, do you have any questions from sir's class or from any other part of this um, lecture that has already been done? Okay, just tell me one thing, how many of you has already read the metric space as well as know a little bit about topology? You can raise your hands. How many of you has done metric space as well as, okay, okay, three. So so those three people, so had you done your topology or metric space course by yourself, or was it a course in your college or university? Okay, that's good. And what about other two?
I follow the Nakahara actually.
Okay, and what about other one? Okay, that's good. Okay, okay. So these three people who already know about the subject. So you have done the metric space course or you have done the topology? Why I'm asking this, because sometimes topology course include metric space and sometimes metric space has separate course from topology. So specifically you have done topology or specifically you have done metric space? Which one? Please write in chat. Okay, and what about the other two? What about the other two? Okay, okay. So my last question is that, so in metric space how much you have done? So you have done compactness, connectedness, or you have done beyond that also? I mean path connected, locally compact, all those things, or okay, okay. Hmm. What about other two? How much have you done? Okay, third sem. Okay, okay, connectedness. Okay, so okay. So can you please can you So those three people, can you please mention which book are you following? Any specific book, or are you um, reading from? I mean, did you in the college which book you followed, or which material, or you just gone through some lecture videos? Okay, Apostle. And what about other one? Royden. And there is one more person. Yes, learned. So from where you have learned? I mean, which material you have followed? Royden. Okay. Okay. So uh, okay. So first, let me tell the good material for this topology course. Sorry, for the metric space course at least. Okay, first, can you please confirm whether the do I need to zoom the whiteboard, or do I need to zoom out, or is that fine?
So I think it's fine for now.
Okay. Okay, so first let me tell some good reference material, so you can follow these following books for metric space only. I mean, of course, this book only for metric space right now. Okay, metric space, S. Kumaresan. So this is a metric space S. Kumaresan book. You can um, I mean, so this book is possibly the one of the very good book out of the others. And if you can thoroughly finish the book up to compactness, connectedness, then I am sure you will understand the grasp of topology. Okay, and the main advantage of the book is that this book is written from sketch, so you can easily follow the book. So this is one very good material for the metric space course. And of course, for topology there are many books, but since okay, but so for metric space this is the S. Kumaresan book, and for and for um, and for topology the book is there are two books. One is of course Mancres, and second is Dugunji. So these are the two books, Mancres and Dugunji. So you can follow this book simultaneously, because there are some things, some materials which are not in Mancres, but there are those things are in Dugunji, and vice versa. Okay, but if you completely finish these two books, then you will be 99% done in points topology. Okay. And one more thing, tell me, those who have joined today, anybody are trying to sit any competitive exams, or okay, which exam? Of course, NET or GET, or in which one, or three? Okay. Hmm. Okay. Okay, so for those competitive exams, this points topology 1 course will be somehow somehow helpful, but not that much, because but that because that exam does not contain much questions from that. So you can better practice more and more Kumaresan and metric space books. Okay. So this is the thing, and okay. So now okay. So now we can start from the definition of metric space. 1 minute. Okay. So what small? Okay. If you feel that the screen is too much small, you can tell me. I will zoom. Metric space. So so suppose x is a non-empty set. Okay. Let D be a function on x cross x to R satisfying certain properties. Property 1 is d of xy is equal to d of yx. So this is quite obvious thing to have, I guess. 1 minute. Yeah. So d of yx is equal to d of xy. Second property is d of xx is equal to 0, and the third property is a triangle inequality. D of xy plus d of yz, this thing is always greater than or equal to d of xz. So if there is a function d from x cross r satisfying these three properties, then we will say d is a metric on x and xd is a metric space. Okay, so we can say like that. Okay, and of course in practice, we simply say x is a metric space. Okay, so this is the thing. Like G is a group, we don't mention any group operation. So okay, so let's see some examples. For example,
Sir,
yeah, tell me.
could you change the red ink into something like,
Okay,
sort of,
sorry.
yeah.
Okay, now is that fine? Now this line.
Sir, could you like something close to white, like which would be more contrasting? Yeah, that would be
Okay,
better.
1 minute.
Mm.
Then is that fine?
Yeah, this is the best, I think.
Okay, let me bold it also. Okay. So okay, so now so of course, so we'll start some examples. So so the easiest example is we can start x equal to r, and we can define d of xy to be mod of x minus y, distance to x minus y, and of course d satisfies all those properties 1, 2 and 3. It satisfies those three properties. So in that case we can say that R with that modulus is a metric space. Okay, metric space. Sorry. So that is the thing. Similarly, if we can take x equal to Rn, so we can take points x1, x2, xn in X. So and we can define d of xy to be the equivalent distance I is equal to 1 to n put over xi. Sorry, there is a mistake. xi square minus yi square whole under root. So this is the so of course, so this is the distance, and this satisfies those three properties 1, 2, and 3. So Rn, the Euclidean distance. This is so this type of distance are known as directly one can say Euclidean distance.
Sir, there should be a xi minus yi whole squared, right?
1 minute. Xi minus y whole correct. Correct. Thank you. Okay, so this is a metric. So basically on r to the power n we can define metric on for all n. So these are something known. Now 1 minute. Okay, so let's start with some examples which are not directly usual. So take x equal to r2. Okay, so points can be written as x1 of x, sorry, so we can write a points x1 x2 and we can call it x. Okay, now we are defining dxy to be mod of x1 minus y1 plus mod of x2 minus y2. Okay. So one can check that this function d satisfies this property 1, 2, and 3. Those three properties satisfied by d, obviously. I mean, you can check. I mean, of course, it will satisfy. So I am not going to check that. Okay. So this also defines a metric in R2, and this metric is known as Taxicab metric. Why the name? Because if you so if you look into the way the metric is defined, you can see that so there are 2 points x and y. This is x1 y1 and this is, sorry, it should be x1 x2. So x1 x2 and this is y1 y2. Okay, so how this d is defined? D is defined in mod x1 minus y1 plus x2 minus y2. So so this will be what? So that d will be nothing but, this distance plus this distance. So this will be so that is our d. So that is our dxy. So that's why this known as Taxicab metric. So this is one metric, and our usual Euclidean metric is what? Euclidean metric is just a straight line. This is the Euclidean one. This is the Euclidean metric. Okay. But interestingly, we can define many metric on this. So we will see soon. Okay. So we will see the example soon. Before that, we have some more examples. So till now we have what I have seen. Till now I have seen that on real line, apart from the Euclidean metric, one can define another metric known as the Taxicab metric. It is basically the distance between those 2 points is equal to nothing but distance between their x coordinates plus distance between their y coordinates. Okay. So this example I have defined for. So this example I have defined for x equal to r2. We can define this. We can do the same for x equal to rn. So let me write it down. So we can take x equal to Rn, and so we can define a point x1, x2, xn to be equal to x, and we can define d of x y to be summation I is equal to 1 to n mod xi minus yi. So this will give a metric. So this will give another metric on Rn. Okay. Now, okay. So this is the thing. So now let's go some usual another examples also. So suppose x be some non-empty space, and we can define d of xy to be 1 if x equal if x equal to 0 if x equal to y, and 1 if x not equal to y. Then d is a metric on x, and it is called what? It is called discrete metric. Okay, and this is called discrete metric. 1 minute. So okay, so I am not checking that this d, which is only 0 when x equal to y and other one is 1, I am not going to check that this is going to satisfy those three properties, but you can check and you can see that this will satisfy those three properties. Okay, so this means what? So this tells that if we have any non-empty space, any non-empty set, on that set we can define at least one metric known as the discrete metric. Okay, so now till now do you have any question or a doubt or any confusion? Till now, anybody have any question or doubt?
No, sir.
Okay. 1 minute. Okay, so now we shall go with some non-trivial things now. So suppose x1 d1 and x2 d2 are metric spaces. Okay, then x1 cross x2 comma d will be metric space. So let me define d, where d of x1 x2 comma y1 y2 is equal to d1 of x1 y1 whole square plus d2 of x2 y2 whole square under root. So this tells that if we have two metric space, on that we can define another metric defined as follows. So I mean, of course, so this formula tells at least the on equivalent case this is the case. Okay, so and of course you can check that that d will satisfy those property. Okay, so so um, everybody is are everybody understanding whether this is this new D. So will this new D satisfy those three properties or not? Is it clear to everybody whether this new D, which we are claimed to be a metric or distance, actually satisfy those three properties 1, 2, 3? Please let me know.
So 1 and 2 are like seem obvious, but the third one isn't so obvious yet.
Okay, that is the triangle inequality, right? Okay, so
Mm.
one minute. So okay, so for triangle inequality, we need to show. So that is what we need to show. We need to show that. So we choose 3 points x1, x2. Okay, x1, x2, y1, y2, and z1, z2. 3 points, and we need to show d of we need to show d of x1, x2, comma y1, y2 plus d of y1, y2, comma d of z1, z2. This is greater than or equal to d of x1, x2, comma z1, z2. Okay, so this is what we need to show. Okay, so for that, what we will do, so this is basically implying what? So this is basically we need to show what? We need to show that x1 minus this is d, it should be d. Okay, so d of x1 y1 whole square plus d of x2 y2 whole square plus root over d of y1 z1 whole square plus d of y2 z2 whole square. This thing is greater than or equal to, we need to show root over d of x1 z1 whole square plus d of x2 z2 whole square. Okay, sorry, we need to write, so there is some d1 d2 is involved. Okay, d1 d2 d1 d2 d1 d2. Okay, so now we need to prove this. Okay, so how to do that? Okay, so what you can do is that we can squaring the left side first, squaring this left side only. Okay, so the left side squaring, what will give? Will give d1 x1 y1 whole square, d2 x2 y2 whole square, d1 y1 z1 whole square, d2 y2 z2 whole square plus 2 root over d1 x1 y1 whole square plus 1 plus d2 of x2 y2 whole square multiplied by d1 of y1 z1 whole square, d2 of y2 z2 whole square. So this will be the thing. Okay, so now I mean, so that's only the square on the left side will give this. Now okay, so can anybody remember the Cauchy squares inequality? The Cauchy squares inequality. There is one fellow from statistics, right? So can you remember Cauchy squares inequality? Anybody can remember Cauchy squares inequality? Because we have done the metric space. Sorry, you have done the point nominal spaces in the class, right?
Yes, sir. Remember it, sir.
Yes, yes, yes. Okay, so Cauchy squares inequality, the statement is as follows. So the statement is summation I is equal to 1 to n ui vi whole square. This is always less than equal to summation I equal to 1 to n ui square into summation I is equal to 1 to n vi square. Okay, so this is the thing. So now we need to apply the Cauchy squares inequality in our situation. Okay, so for that, obviously one can guess that for we put this thing to be our ui, and for this part we put in our the vi thing. Okay, so this Cauchy squares inequality now give the following. So by Cauchy squares inequality, what we're getting is that this root over d1 of x1 y1 whole square plus d2 of x2 y2 whole square into root over of d1 of y1 z1 whole square plus d2 of y2 z2 whole square. This thing is greater than equal to d1 of x1 y1 into, okay, so there no space here, so this thing greater than equal to d1 of x1 y1 into d1 of y1 z1 plus d2 of x2 y2 into d2 of y2 z2. So this is the thing. So by Cauchy squares we can write that, correct? So now if we apply this inequality there, what we will see get? So remember that this left hand side, after doing a square we'll get this, and so this left hand side after doing a square we get this, and then okay, and then we see that that left hand side thing is greater than equal to so this thing is greater than equal to something. Okay, so now we can apply all together, and finally we are getting the following, namely, so what was that? It was d1. Okay, so okay, so we see that this thing, so this thing, if we call it big Y, then this big Y is greater than equal to, then this big Y is greater than equal to, what is this big Y? Big Y greater than equal to d1 of x1 y1 square plus d2 of x2 y2 y square plus d1 of y1 z1 square plus d2 of y2 z2 square plus 2 times of d1 of x1 y1 d1 of y1 z1 plus 2 times of d2 of x2 y2 into d2 of y2 z2. Okay, so this thing is equal to what? This thing is equal to d1 of x1 y1 plus d plus d1 of y1 z1 this whole square plus plus d2 of x2 y2 plus d2 of y2 z2 whole square. Okay, so this tells what? This tells that okay, so now now observe that D is a metric, D1 D2 metric. So what? So of course this particular thing is anyway greater than equal to D of x1 z1, and this particular thing is greater than equal to d2 of x2 z2. So this whole thing is greater than equal to d1 of x1 z1 whole square plus d2 of x2 z2 whole square. Okay, so we need to look at our root over y, because y is our squared candidate. So root over y is greater than equal to what? This is greater than equal to d1 of x1 z1 plus whole square plus d2 of x2 z2 whole square. Okay, so this was the argument. Do you understand, or it just got messed up? Tell me please.
Yeah, sir, it's clear now.
Okay, so the main trick was that you need to apply the Cauchy-Schwarz inequality only, and rest it will come automatically almost. There is nothing to really calculate. Understand? Okay, now
Sir, can I ask a question from the assignment of week 1, like something like this?
okay, so assignment of week 1, what is the submission date?
Date 5, I think.
February 5, right? So after
Yeah.
that only I can answer that assignment. Okay.
But like, could you give some idea, not the
Yeah,
direct
okay.
answer, but
Yeah, okay, tell
hint
me.
or something?
Yes, tell me.
I think it's from question number. Let me check the question. Question number 4, the fourth question.
What?
Define D. S1 cross S1 to R by the formula d of e to the power twice by I by 1 theta 1 comma e to the power twice by theta 2 is equal to 1 minus cos of theta 1 minus theta 2.
1 minute,
So
please. 1 minute. Let me open the question itself. 1 minute.
mhm.
So that is subjective question, right?
It's
It is
yeah,
quiz.
true.
True or false? Okay.
Yeah,
One. So you are asking about that fourth question. Okay.
yeah. How do I check the triangle inequality? Like 1 minus cos of.
Cos. Wait. So first, so it's a true false question, right? So why you think that it will be a metric? Firstly, I mean, why you think that it will satisfy the triangle inequality?
No, I'm yet to find out like whether it satisfies or not. So I try to see if it satisfies.
Okay. So firstly, okay. So just tell me one thing. What is your approach? Your approach is just to do the calculation, or you are thinking at least geometrically or intuitively?
Uh, so I didn't think in that line first. I just wanted to check if it satisfies the axioms of a
Okay.
metric.
Firstly, let me tell that this is not metric, because this will not satisfy the triangle inequality. Okay.
Mm,
So this is the answer. But you need to understand that by looking into the situation, that how this theta 1 theta 2 corresponding to the distance. Okay,
mm,
in the by plotting at least some few points. Okay, if you plot, you will see actually there is nothing complicated there. But in order to get the
mm,
intuition whether it is satisfying triangle or not, you need to plot the graphs of the with respect to theta 1 theta 2. Okay, I mean, of
mm.
course, specifically I can tell which theta 1 which theta 2 it will fail, but there is no point. Understand?
Mm.
So it will not satisfy it, the triangle inequality. You need to realize that by looking into the picture.
By
Understand?
plotting point and checking.
Haha, yes, plotting points.
Okay.
Okay.
Mm.
Um, okay. Any more questions?
Uh, then I tried. That one's uh, the second one, sir.
1 minute.
Like the first one, I found that every vector has a norm. Yeah, I constructed some. But for the second question, like V is a vector space over K,
One,
W linear subspace.
one.
So can we extend a norm on subspace to a norm on the whole of V?
Which question?
Second questions.
1 minute, please. Why is not opening? 1 minute. Okay. Yes. So let me space. So space. Mm, 1 minute. Okay. So for second question, what is your question? I mean, what is your doubt in the second question? How to solve this, or how to get the metric?
My doubt is like, can we always extend a norm on a subspace to a norm on the whole of the ambient space, the bigger space?
Yes. It is possible always.
Mm,
Now it's now point is that this particular question is somehow uh, part of function analysis at its basic. Okay. So the
mm,
point is that if you have not done that course, or if you have no idea of those things, so it will be difficult for you. Okay, I can explain the answer right now, but as far as the instruction before assignment deadline. I am not allowed to do that. Okay, so after
Okay, sir.
5th, I will explain how this will be. Okay, understand?
Yes, sir, no problem. Yeah.
But one obvious way, let me tell you, one obvious way is to extend that. You can do the sum. Suppose you already have some metric on a bigger space. Okay, and now you gave you some define some new metric on the smaller subspace. Then on the bigger space you can define another metric by taking the sum of the, sorry, I mean norm. On the bigger space you can define a norm by taking the sum of two norms, that one is the norm coming from the smaller subspace, another is the norm coming from the bigger subspace. You can just take the sum of that. Okay, so that will be the idea, but precisely right now it is not possible to tell.
Okay, sir, no problem. Yeah.
And any more questions?
No, sir, only these two so far.
Okay, so
Yeah, could you repeat like sum of two norms? Like suppose we have W as a subspace of V,
yes,
and if we have a norm on W, say norm 1,
yes,
so we take the sum of this norm and which other norm?
you have some norm on the smaller space also, right?
Mm.
Now you can take the sum of the smaller, I mean you can define some norm which can,
Mm.
I mean suppose you choose a point from the bigger space. Okay,
Mm.
and suppose that point contains a part from the smaller space. Okay, that might be possible, correct? Suppose the number is 1 x plus y. Suppose y belongs to u, it might be possible, right? I mean smaller space u. So in that case we can define norm of x comma y or x plus y to be norm of x plus norm of y with respect to the given norm on the smaller space u. Okay, so in that way you can define. Now you need to make it precise, so think about it. Okay, how to do that without, I mean you little bit need to use linear algebra and function analysis.
Mhm.
Understand?
Uh, okay, sir, I'll think about it.
Yeah.
Thank you.
So one minute. Okay, so okay, so what we have seen is that till now, so okay, so over Rn, so what we have, so basically what I've seen is that if we have two metric space, we can define the metric on the Cartesian product. So this is only, where is that? So this is only why it is not going down? What is it? So okay, so this is one possible way to define a metric on the given space. Okay, on the product. So there are other possible ways. So let me demonstrate that. So so let me demonstrate it. How to? Okay. So suppose we have again two metric x1 d1 and x2 d2. Okay, sorry, d2. We can define another metric d on x1 cross x2 as follows. How? So d of x1, x2, comma y1, y2, we are defining it to be d of x1, d1 of x1, y1 plus d2 of x2, y2. So check that check D is indeed a metric on where on x1 cross x2. So you can please check it by yourself that D is a metric on x1 cross x2. Okay, please check it. Please do it by yourself. I mean, of course, you need to only satisfy triangle inequality. There is nothing to do, but please convince yourself that this new D will be another metric. I shall come after 2 or 3 minutes. Okay, please try, and if and after coming back I shall explain. Take your time and please try. Okay, so um, let me know. So are you able to convince yourself that this new D is a metric?
Yes, sir.
Okay, that's good. Okay, so now, so this is one new metric. Now we'll see that another possible metric one can define also, namely, namely, we can define another D of x1, x2, comma y1, y2 to be uh, to be d1 of x1 y1 to the power p plus d2 of x2 y2 to the power p whole to the power 1 by p for any p is an integer. Of course, p is a positive integer. Okay, so this will also be this will also be a metric. So this will also a metric, and here the main trick is Cauchy-Schwarz inequality. For what? For the triangle inequality, for showing the triangle inequality. Okay, so you only need to show this Cauchy-Schwarz inequality. You need to use that, and you can show that this new D will satisfy the triangle inequality also. Okay, so till now, so basically what we are doing is that so they are a given metric, and on the given metric we can define, we can define many matrices on the Cartesian product. So these are the three we have seen. So till now, is it clear to everybody?
Yes, sir. Yeah, this tree.
Okay. So now, now one more metric we are define, namely d of x1 x2 comma y1 y2. We can define it to be max of d1 of x1 y1 comma d2 of x2 y2. We can define this, and now you can now check that D is a metric. Okay, please check it by yourself that whether D is a metric or not. Okay, so basically we just take the maximum one and we are claiming that it will satisfy those three properties. Please take your time, please try to convince yourself that this our new D, which is the maximum, will satisfy also the triangle inequality. Please take your time and let me know. Okay, and if you have any doubt you can ask. Please take your time. And if anybody is done, please let me know.
D of next to y1 y2 max something. Y2 max of d1 x1 y1 d2 x2 y2 plus max of z1 d2 x2 plus max of
So, are you able to convince yourself that whether the new D will define will satisfy the triangle? Sorry, are you able to convince yourself that the new D we have defined will satisfy the triangle inequality? Let me know.
Sir, how the D1 and D2 are defined?
I mean, so okay. So x1 d1 is a metric space and x2 d2 is another metric space. So d1 and d2 represent the associated metric with the space x1 and x2.
Okay.
Yeah. First, try to convince yourself that whether that d we define as a max of d1 d2 will satisfy the triangle inequality. Of course, you need to use the fact that d1 will satisfy triangle inequality d1 d2. You need to use that fact. And I mean, so if so, I mean, so start writing it, then I think it will come immediately. Please take your time and let me know.
Sir, I came up to the point where I wrote the triangle inequality of both D1 and D2.
Hmm.
Then, by looking at the left hand side, I mean, like for the first one, I wrote D1 of x1 y1 is less than or equal to D1 of x1 z1 plus D1 of z1 y1.
Correct.
For the D2, I wrote D2 of x2 y2 is less than or equal to D2 of x2 z2 plus D2 of z2 y2.
Correct.
We have these two inequalities.
Yes.
Now,
Right.
if I look at the left hand side and compare those, and if I pick the maximum of those two,
Mm-hmm.
it will be less than or equal to the maximum of the first two terms on the right hand side. I mean the like the left two terms
Mm-hmm. Yes. Yes. Yes.
plus the maximum because I'm choosing the maximum in its case, and
Yes.
that comes up to be the triangle inequality for this new metric.
Yes. Yes. Correct. Right. Very good. So, I mean, of course, so whatever it is done, so there is nothing to discuss at least metric or okay. So metric now.
Mm.
So this button. So okay. So basically, what we have seen till now, that is on on a given space one can define more than one metric. Okay, so a natural question then one might think that whether is there any, I mean whether is there any connection, or we can tell that two metric are basically same or not. Is there any notion like that? The point is that yes, there is a notion under which we can say that two metric are equivalent if and only if something occurs. Okay, but right now we are not in that right position to define the notion, so for that we need to wait few more sessions. So so that is one thing. So these are the examples. Okay, so now having done this, we can define the most fundamental thing in the metric space going to whenever we are looking at topology, namely is the open ball. Okay, 1 minute. What happened? Why is not? Okay. So this is the open ball. Okay. So of course, what is the definition? Suppose x. Okay. I mean, of course, I assume that everybody knows the definition of open ball, but just for sake of completeness, I am writing this. Suppose xd be a metric space. Okay. Take x belongs to x, and suppose r greater than 0. We can define brx, that is, so brx to be all those y inside x as a d of xy less than r. Okay, so basically what is this? It is basically nothing but 1 minute. Oh shit. 1 minute. So what is this? Is basically nothing but so it is defined here we have x and this is the radius r, and all the point will inside the ball of radius r. So this is nothing but brx. Okay, so while calculating or while doing theoretical proofs in metric space, we can use this ball radius notion, at least to think intuitively. Okay, so this is then, so and this is known as open ball. This is known as open ball around x of radius r. Okay, so this is one thing. So this is open ball. Okay, similarly one can define closed ball. What is that? So in open ball we have seen the definition of the open ball. In the definition of open ball, here d of xy is less than r. There is only less than, there is no less than equal to, right? So the closed ball is same thing, where we only the less than equal to sign will be there. Okay, so that is this closed ball we will denote by this box of x. All those y belongs to x as the d of xy less than equal to r. So this is called as the closed ball around x of radius r. Okay, 1 minute. So this is the thing. So this is closed ball. Okay, now so now the immediately one can, now we are in a position to define open set. Okay, so since some of you has already started material space, so can anybody please define the open set? Of course, if you forgot some portion, that's no problem, but you can at least unmute yourself and tell what does this mean by open set. Please take your time, think about it, and let me know. I shall be back after 1 minute. Okay, anybody able to recall what does it mean open set, or what is the definition? Okay, okay, so let me give the definition first. Okay, so so let u subset of x, okay, then u is said to be open in x. This is extremely important. Open in where? Open in x. If for any x belongs to u, there exists an r greater than 0 such that b are x subset of u. So this is a definition. That is, so intuitively, what does it tell? It tells that we have some u, okay. So this is u, and suppose we choose a point x. If we are able to get an open ball of radius, some open ball of some radius inside which lies in a hole inside u, then we can say that u is an open set, okay. So this is a definition. That is, for any point, if you are able to get some open ball which is contained entirely inside capital U, then we can say that U is an open set, okay. So that is the thing. So now, so this is the definition, okay. So just now we have defined open ball, right? So now prove that open ball is an open set. Prove that. Prove that open ball is an open set. It will not be difficult. Just try to prove it. I mean, you need to move along with the definitions only. So what you need to consider open ball. You need to choose any point in this open ball. You need to show that we can able to manage another open ball around that point inside the big open ball. Of course, intuitively that is true, but how do you make it mathematically? Think about it. So how are we able to show that if we take any open ball, then if you choose a point, then you can get an open ball inside the big open ball. That is, what you need to do is the following. So you have some big open ball. Okay. And suppose x, it is an open ball around x. Okay. Now what you need to do, you need to choose some point y, and you need to show there is an open ball around y such that that ball lies inside the big ball. How to do that? So I mean, it's not difficult, of course. So what do you do? So you can,
So we can choose some delta to be less than r minus distance between y and x.
okay, correct, right. So you can choose the delta to be r minus distance between y and x, and then the ball around delta will lie inside ball around, sorry, ball around y. Sorry, by delta subset of brx, and this can be done for all x. So this tells that, this tells open, so brx is an open set. Okay, so that is the thing. Now so this is open ball is open set. Okay, now proofs of few things show that. Okay, so let u alpha be an arbitrary collection of open sets in X. Show that union u alpha is also open. So basically this question, suppose you have an arbitrary collection of open sets in X, you need to show that union is also open. How to do that? Of course, it is not difficult, it is very easy. It's just looking, the statement wise it seems difficult only. Just think about it. What you need to do, you need to choose some point and then you need to get some open ball around that point, inside of which lies entirely inside the union of u alpha. Now how you can do that? Think about it. Think about it, take your time. So what you need to choose some point from the union, and you need to find an open ball which is like around that point which lies entirely inside the union. How we can do it? Think about it and let me know. I shall wrap for 2 minutes. Anybody, please? Anybody? Okay, so let me explain 1 minute. So what you need to do, you need to you need to choose some x inside the union of u alpha. So this tells what? This tells that x belongs to u alpha naught for some alpha naught, right? Correct. Now it is given that u alpha naught is an open. So this implies what? We can get r greater than 0 such that Brx, this open ball, can lie entirely inside u alpha naught, and of course this u alpha naught is a subset of union of this, I mean this arbitrary union. So this implies what? That Brx will subset of union of u alpha. So this tells that what? This tells this union u alpha is an open set in. So this is an open set in where? In X. Okay, so this is the way. Do you understand the argument? So basically what we need to do, we need to, so whatever we choose some point, and since it is union, so that point will lie inside some of u alpha naught, and we take the advantage of the situation that each u alpha naught is an open, and so we can get some open ball inside the u alpha naught, and that open u alpha naught lies in union of u alpha naught. So this is the argument. Do you understand?
Yes.
Oh. Okay. So okay, so this is the thing. So now of course now one might ask what are the intersection, but let me tell you, for intersection, the arbitrary intersection might not be open. We will see some example, but before that let's see the following. Let's try to prove the following. Let ui be finite collection of open sets in X. Show that intersection ui is also open. So the finite class u alpha of open sets, we need to show the intersection ui is also open. Okay, find intersection of open sets open. This is what need to be proved. So how we can approach that? So the same way, choose a point inside X and we need to somehow get some open ball which lies entirely inside the intersection, that is which lies in each of the ui's. So how we can do that? Think about it. At least you can, so for open ball you can consider the circle and the points, you can take the description and try to think that how you can able to get some point which lies inside each u alpha. Think about it. Take your time. Anybody, please? So this is not difficult. I mean, what you need to do, you need to check some point, you need to get some open ball under that point, and you need to show that that point will lie inside entirely in all UI. So how to approach this problem? Don't try to mug up the argument. First, try to understand how this argument works. Okay. So
So the idea is that
yeah,
the minimum of a finite set will be the minimum of a finite set of positive quantities is positive. I think that should do it.
sorry, a minimum
Of a finite set of positive numbers is positive. So it's a finite collection, right?
yes,
So from there, I think we can choose a minimum of the R's.
yes, correct, very good, right. So basically, so this is as follows. So choose x belongs to intersection ui. It's a finite collection, so this implies x belongs to ui for all I belongs to 1 to n. Since each ui is open, so there exists ri greater than 0 such that bri x subset of ui. Now choose r is equal to minimum of r1, r2, rn. R1 to rn, and so we can then b of rx, which is subset of brix, this will be subset of ui. So this implies that brx subset of intersection ui. So this is the argument. Okay, so this is the thing. So yeah, so this is the argument. So I hope everyone understand. So I mean, does everyone understand this argument? So basically what he told is that need to choose the minimum of all radius, so that ball will lie inside all the balls coming out of the openness of each ui. So that is the trick, one can say. So now, 1 minute. So now so now show that open, so that arbitrary intersection. So we have seen that finite is opens are open. We are eager to show that arbitrary intersection of open sets are not open. So I mean, we are not going to. So basically, we are providing counter examples. So anybody, please.
Shavik need not be open. The arbitrary intersection can still be open, no?
Sorry.
It always need not be open.
Yeah, sorry. Yeah, yes, correct. So arbitrary intersection might not be open. So the arbitrary intersection of open sets. Yeah, so thanks. So anybody please provide some counter example? I mean, anybody please provide some example which shows that arbitrary intersection might not be open. So you don't need to go in the metric space also. You can find that example in real n itself with the usual Euclidean metric. And of course, I have seen that I mean, of course, I'm sure that you have seen that example in reanalysis also. Just try to construct the example right now. Anybody please? I mean, of course, this is very easy counter example. Anybody please tell? Unmute yourself and you can tell the counter example. Of course, you have seen the same as reanalysis, right?
We can take a sequence of open sets defined by -1 by n, comma 1 by n.
Sorry, -1 comma.
-1 upon n.
Oh, sorry, 1 minute. Okay, then
Comma 1 by n. Yeah.
1 by n.
Oh, sorry, no, not this. We can,
I mean, why not this?
because the intersection will be closed, singleton.
That is what we need to show, right?
Oh, not open. Yeah, sure.
Right. So yeah, so this is one counter example. Its intersection is singleton 0. So that's okay. So that is the thing. So and of course, one thing I must say is that, I mean, which is quite obvious, but at least I should point out is that, so if XD is a metric space, so if XD is a metric space, then the empty set and the whole space is also open set. And I mean, this statement is vacuously true, so there is no need to prove this. Okay. So what I've seen is that, suppose if we have some metric on a given, suppose there is a metric defined on some capital X, then it satisfies 3 properties, namely one is the empty set and the whole space in open set. This is first. Secondly, arbitrary union open set is open, and thirdly, finite intersection of open set is open. So these 3 properties, okay. So these are 3 properties in the metric space. Now you might think that why I am suddenly talking these 3 properties, because when we go to topological space, so the topological space is defined as a collection. So suppose X is any non-empty set, and suppose there is some suppose there is a collection of subsets of capital X satisfying these 3 properties, then we can say that X has a topology on it, and those sets, those collection of subsets of X satisfying those properties are known as the open sets. Okay. So we'll see those things after few days. Right now, just keep in mind that matrix will satisfy these 3 properties. So matrix space is a topological space. Okay. So of course, those who know a little bit of topology, they might ask how to define the topology, or how to define the topology, all those things. The point is that we have seen that open ball is an open set. Okay. So this, I mean, so the topologies are only the topology of X only constitutes of topology on X only the collection of all the open sets on X. So this is the thing, and this topology is known as the okay. So this topology is usually known as the metric topology, because these open sets we are getting are coming from the given metric. And okay, so one more. So So okay, there is nothing much to say regarding this metric topology. We will see later that there are some beautiful properties on the metric topology which satisfy, but the usual topology shall not satisfy. Okay, so okay, so do you have any questions till now, or any doubt, or any clarification regarding this live session, or any clarification regarding this course, anything, or do you have any suggestion? You can unmute yourself and tell. Or do you have any specific question in your mind?
I think we can focus more on problem solving, right?
Of course, of course. Okay, okay. So 1 minute. So 1 minute, please. Okay, so uh, okay, so okay, before study probably we need to define a few things, namely the closure of a set and all those things. For this we need to, there are, I mean, so suppose A be a subset of capital X of some, sorry, so of some metric space. So we can define the closure of A, which is denoted by A closure. So anybody can define the closure of a set? I mean, of course, I mean, you can unmute yourself and tell, but closure of a set is basically all those X belongs to X, such that for any real number greater than 0, BXR intersection A, sorry, why it is not working? BXR intersection A is non-empty. So this is why we mean the closure of a set. Okay, so this is one definition, and there is another sequential definition, which we will see in the next session. And so this is one thing. And moreover, by closed set, suppose F subset of X, then X is said to be closed, if its definition, if X minus F is open in X. Okay, so these are the some few things, and of course, just writing down the some few properties of these closed sets. That is, firstly is that arbitrary, just one can prove this by using definitions. Arbitrary intersection of closed set is closed, and finite union of closed set is closed. So these are the few, and of course, nevertheless, phi and X, I mean the whole set and the empty space, will also be closed. Closed in where? Closed in X. Okay. So these three properties will satisfy the closed sets. Okay. So in some situation we might see in the course that topology on a given space can be defined in terms of closed sets also, that is in terms of these three properties. Then we can define those subsets of X satisfying these properties defining to the closed set, and the complement we can define to be open set. So this is another way of defining a topology in a given space X. And of course, so there is one more thing, is that convergence. One is notion is the convergence. So of course, so there are many, I mean, so of course the converse, the sequence, convergence, subsequence, there are those notions analogous to real analysis there in the metric space also. So can anybody please tell that whether do I need to go with the convergence, or we can directly jump into the problem solving for the next session? I mean, is there anybody here who does not know this convergence, at least for basics? Anybody please? So does everybody know the convergence? I mean, please don't keep yourself mute. Okay, if you don't know, please tell that you don't know. If you know, then also please tell.
I think it's better to cover the first 10 minutes for those who don't know yet, and then you can start the problems.
Okay, that's good. That's good. Actually, good
Yes.
session. Okay. So, okay. So, okay. So from next session we shall start the convergence, and then we shall go with the problem solving. Okay. And so that is my plan. So okay. So today we are finishing here. So we shall meet in the upcoming Friday from 7 to 9 with the same joining link will be there. Okay. So that's all for today. So does anybody have a question or any comments or any suggestion? Any suggestion or any comment or any questions? Okay. So if you have any question, you can post in the group. I will reply as soon as possible. Or if the question is something like that is not possible to reply over email, then I can discuss that question in the upcoming sessions. Okay. So that's all for today. Okay. Thank you for attending. I am leaving the session.
Thank you.